Great. Thanks so much to the organizers for the invitation. It's a great workshop. Really enjoyed all the talks. This talk is based on joint work with Parikshit Shah, who's at Philips Research. And it's about, it's part of a broader project, I guess, but I'll focus on one interesting component of it in our review, which is to try and explore the computational properties or computational aspects of the relative entropy function. So this function has many beautiful, interesting properties that are used to prove all sorts of interesting things in information theory and statistics and so forth. But this talk is about trying to exploit the joint convexity of this function from a computational perspective to solve some interesting problems. So the specific problem that I'll focus on today is that of Signomial optimization. So a Signomial is a function of the following type, where I have sums of exponentials composed with an affine function of a variable x. And this parameterization, this problem, or these functions and the associated optimization problems are non-convex. You can reduce families of NP-hard problems to examples of Signomial optimization problems. A subclass that some of you may have heard of is geometric programming. This is a situation where all these coefficients are positive. So you have a positive sum of convex functions. So you end up with convex optimization problems, a term that's used a lot in that literature. These positive sums of exponentials are sometimes called polynomials also. And so in geometric programming, you minimize a polynomial, a convex function, subject to upper bound constraints in polynomials, so convex constraints. So those problems end up being tractable to solve, but in general, when you have arbitrary signs, pluses and minuses, these things get more difficult, get more challenging. One application, in fact a broad range of applications in some sense, falls under this sort of general label of network utility.
This includes all of polynomial optimization.
This includes polynomial optimization over the orthant, right? Over the non-negative orthant. And I will actually contrast at the end, make some interesting connections between this and polynomial optimization when perhaps sums of squares-based methods that have been explored, developed in that community, how they correspond to things here. Sorry.
Why do exponentials include polynomials?
So for instance, I could just do a change of variables where, So, I mean, not stated this way, but if you change each e to the xi to yi or something, you're solving a polynomial optimization problem over the orthant.
But if you have other constraints, then you can't do that.
What do you mean other constraints? I mean, I'm just considering problems with exponentials. Only exponentials. No other types of constraints. Yeah, to be clear.
The alphas are all integers.
The alphas are all positive integers. This is a polynomial optimization problem over the orthant. Absolutely. Okay, so one broad sort of class of applications, places where these sorts of problems have been solved, have come up, is in something called network utility management. Meng Chiang at Princeton has done a lot of work in this area. And it's broadly about optimally allocating resources in a network type setting to optimize some sort of performance. So one example that I've seen in this context is to allocate power in some sense across a whole bunch of users to optimize throughput, subject to constraints that specify bounds and signal to interference. I'm not going to go into the details. This isn't my work. This is Meng's and his collaborators' work by them. But the thing that I'd like to highlight is that when you look at these signal to interference type constraints in this context, you end up with constraints on ratios of polynomials. And so ratios of polynomials can be transformed to Signomial optimization problems, Signomial type constraints. And so that's one of the interesting things that you can do when you allow yourself Signomial type inequalities. You can go from just polynomial or upper bound constraints in polynomials to more general types of constraints, rational functions of these things and so forth. And there are a whole bunch of other settings as well. The initial work in this area was done in geometric programming as well as in Signomial programming by a researcher, Peterson, and as well as some of his colleagues. They had some applications involving certain nonlinear flow problems and graphs and so forth. There are control problems that show up in chemical engineering, and this is actually a very prominent class of applications. Fludus has a nice survey article on those sorts of problems. It shows up in mechanical engineering problems as well. but shows up a fair bit in many contexts. Another view of what I'm interested in, a dual view, if you will, if you focus, for instance, in the unconstrained case, is we're interested in problems of this type by sort of a simple transformation. You can also view everything that I'm doing as trying to understand this object, the convex hull of a collection of points where each of these are just exponentials. And so everything that we'll do can be viewed as trying to understand this convex set. So although this is a linear functional, this is a convex set, in general this convex set is intractable to characterize. So although this is a convex optimization problem stated in this parameterization, that doesn't necessarily make sense. Okay? And the main idea in this talk is to develop convex relaxations for Signomial programs based on relative entropy optimization. So for the record, the relative entropy function is defined as follows. And what's very interesting about it is that it's jointly convex over both arguments. And so that joint convexity is something that will play a key role in everything we do. Okay. And the key idea that I'll describe in the next few slides is a connection between the relative entropy function and the AMGM inequality, which is, I'll keep coming back to it a few times, so I figured I'd actually just write it up on the board. And in the spirit of sum of squares based relaxations for polynomial optimization problems, we'll be talking about hierarchies of convex relaxations based on relative entropy optimization now for Signomial programming problems. We'll have examples along the way. And at the end, in the last few slides, I'll sort of talk qualitatively about contrast with polynomial optimization. Okay, so the basic idea with all these sorts of things is when you want to minimize a function, in the unconstrained case, you can also talk about maximizing lower bounds in that function. And effectively, based on this reasoning, you get to the idea that you need some interesting mechanism, some framework, to be able to certify non-negativity. This is true for any function, of course, but I'm specifically interested now in certifying non-negativity of signomials. Okay. Now, in a signomial, if all my coefficients are positive, it's clearly globally non-negative, right? Because I have a positive sum of exponentials, exponentials are positive, and so I'm okay. But when you start having negative signs, things get interesting. The non-negativity question is interesting. So let's focus on signomials with just one negative term. So I have a signomial like this. This part will consist of just positive coefficients. And there'll be one term that could either have a positive or a negative coefficient. And I'm interested in the global non-negativity of the signomial. This is equivalent to, this signomial being globally non-negative, is equivalent to the existence of a nu such that these conditions hold. So such that relative entropy inequality is satisfied for a fixed C and for a fixed beta. The nu belongs to the non-negative orthant, and the system of linear equations is satisfied. And you can show this via strong duality. This goes both ways. But there's a nice interpretation of this via the arithmetic geometric mean inequality. So if you take just the positive part here, and you apply the AMGM inequality with the weights being the nu j's suitably normalized, you get the very first line. And that's just applying this AMGM inequality. If you have a bunch of non-negative guys, that's greater than or equal to this product, where these delta i's lie on the simplex. So those are the weights, and this is a generalized AMGM inequality. So that's the first line. The second line, everything remains the same except going from the Q's to the alphas. Yeah?
I'm just curious about that. It's stupid and it's just kind of reminiscent. It's reminiscent of the kind of tricks you do with Jensen's inequality, but now there's a product instead of a sum. Is there a way to interpret this?
Yeah, it's the log sum exp. It's it's the convexity of log sum exp.
Oh, so you just take log of both sides.
Yeah,
and Jensen. I see.
yeah.
Cool.
That's it. But this, there are many ways to write this, and this way sort of most transparent here. So the Q's go to the alphas because of this relationship, and that's how we get the second line. There's some more inequalities to boil this down to this negative relative entropy, and then the last thing follows by this. So, but the key insight, the key thing here really is that the new j's, the existence of those new j's, really should be interpreted as the existence of a set of weights that certifies an AMGM inequality.
In this case, your weights you can always assume they're a probability measure on the.
No, so that's actually key. These news, so once you normalize them, yes, it's a probability measure, but I'm searching for news over the non-negative orthid, and that is key.
So, is this the case that one direction is always true, but the if and only if is only when there is at most one negative coefficient?
No. The other direction also follows. It's a strong duality argument. You can transform the non-negativity of this thing.
If there is more than one negative coefficient.
Oh no, this all applies to situations where there's at most one negative coefficient, and in that case, it's if and only if. I'll get to the situation with more negative coefficients in a second. But in the one negative, or at most one negative coefficient case, this goes in both. So really what you're doing is that you're searching for weights news, that certify an AMGM inequality and thereby certify the global non-negativity of the Signomial. And it's a reformulation, if you will, a different parameterization of early results in GP duality that go back to even the late 60s.
If you subtract off a term here that just depends on C, then you can assume that the V's are a probability distribution.
If you subtract off a term that depends...
Yeah, like it just depends on the vector C.
Okay. We can talk about this offline.
I just want to know if I should think about something special is going on here because V is not a probability, nu is not a probability distribution.
It turns out, actually, maybe I should talk about this more in detail offline. The early results in GP duality, in fact, did assume that nu was a probability distribution. They explicitly worked with things on the simplex. But that leads to issues that I'll get to in just 2 more slides with, maybe I can give it away. What's nice about this is that it's jointly convex in nu, C, and beta. If you restrict news to be probability measures, a la the early results in GP duality, you don't get joint convexity of this guy in nu, C, and beta. And that's critical for what we want to do later on. And I'll get to that. We'll see that in the next few slides. Okay, so what this does is just to reiterate, is that we're searching for weights that certify an AMGM inequality. But in all this discussion, we've thought of C, beta, and these exponents as being fixed. But now if you just think of these exponents as being fixed, you can actually think of the set of globally non-negative signomials with respect to these exponents. And that set has a nice convex parameterization based on the result that I just described. So the set of all C's that are non-negative and betas, where this is true, can be written in this way. This is certainly a convex set, but via the joint convexity of relative entropy, we actually have a nice parameterization for the set.
So this is a cone, no? Convex.
This is a cone. This is a convex cone. This is a very nice parameterization.
This describes the extreme rays in particular? Or?
The extreme rays are exactly where this is equal, and so the AMGM inequality is satisfied sort of tightly, where it's equality there. Absolutely.
It's an extended formulation for that.
It is absolutely an extended formulation of the set. And I'll actually have a few words to say about that at the end. So this sort of naturally leads to a definition. So we'll call a signomial an AMGM exponential if it's a globally non-negative signomial with at most one negative term. And for such signomials, we have an effective non-negativity certificate via relative entropy in the spirit that I just described. An example, for instance, is this family of signomials. For each fixed epsilon, you can show that this signomial is globally non-negative via the tools just described. To go now to the question that was just asked, to more general signomials that may potentially have more than one negative term, the natural thing to try to do is to decompose a general signomial as a sum of AMGM signomials, because if I'm able to do this, and each term I know can be efficiently certified as being globally non-negative, leads to a sufficient condition now, not equivalent, unlike in this case, but just a sufficient condition for global non-negativity of a signomial. And so that leads to the next definition, which is that of a sum of AMGM exponentials. We'll call these things SAGE functions. And these are signomials that can be expressed as a sum of AMGM exponentials. And a SAGE function, or a signomial being expressible as a SAGE function, is a sufficient condition for that signomial to be globally non-negative. Okay. So this is a simple parameterized example. So A and B parameterize the signomial. There are two positive terms and two negative terms. The exponents are pi over 4 and 1 minus pi over 4, and the same thing swapped. And this is what it looks like. The white cells correspond to this function being a SAGE function. Okay, and this is where it's globally non-negative, at least certifiably so via relative entropy.
A and B as variables?
I'm not thinking of A and B as variables. A and B are fixed coefficients here. This plot tells me all those values of A and B for which that signomial as a function of x is globally non-negative.
So in those decomposition, is one positive term matched with one negative term, or it's all can be more complicated?
Sorry, could you repeat that question, please?
Decomposing this thing
I'm
as a
decomposing this, it turns out, as a sum of two AMGM exponentials.
sum, but does it respect the structure in the sense that one positive guy is always matched with one negative guy?
It usually ends up being that some fraction of these two positive guys is matched with one, and the remaining piece is matched with the other one. That's exactly right.
Is that a necessary? I mean, so it's sufficient for global non-negativity. Like here, you've drawn the plot of where it is a SAGE function.
Yeah, but that's only a sufficient condition. In general, it's not necessary, and I'll give examples.
You know, in this picture where it's non-negative?
In this picture where it's non-negative, I think it's not this. It's a bit bigger than this. So that's all I'll say here. But
I guess the question is, if there is a decomposition like that, is it always a decomposition that only uses the terms that are already there, or sometimes you add new gains?
so the way we'll construct this is just by using exponentials that are already there. And I'll get to that. I mean,
But it's not a necessary condition, right?
But
So maybe-
sometimes could be a more complicated decomposition.
what do you mean by more complicated decomposition?
Doesn't use terms that are already there.
What do you mean by terms that are already there? I'm a bit unclear. Sorry?
Exponentials.
So I could add more exponentials? Add and subtract.
Yes.
Yeah. You could in general do that, and that in general can be helpful. In what I'll describe, we'll just stick to SAGE functions with respect to just a fixed set of exponentials, i.e. the exponentials that appear in our signal. But in general, you could add exponentials with zero coefficients, and you can actually do a bit better. And I don't have examples of that here, but I'm happy to talk about that offline. Okay, so formally, actually relating very much to the point that was brought up, let's fix now a set of exponents. The set of SAGE functions with respect to these exponents is a convex cone, and that set is described as follows. It's all functions written in this way. Notice that the number of terms here is exactly equal to the number of exponentials, and each fi is going to be an AMGM exponential, where the ith coefficient is allowed to possibly be negative. Each fi, globally non-negative, and it also is written in terms of those exponentials. And with the exception of the ith coefficient here, everything else must be positive. Okay? So this answers your question, where at least when we define SAGE functions, we do it with respect to a set of exponentials. And each of these fi's can now be certified to be globally non-negative in an effective way via relative entropy. All right, so now if checking SAGE decomposability with respect to a set of exponents is a relative entropy program in the coefficients of your signomial, this is something that's convex efficiently solved, and it leads to a natural relaxation, a natural convex lower bound for unconstrained SPs. Very much in the spirit of what I described a few slides ago, very much in the spirit of sum of squares based lower bounds for polynomial optimization. So I can fix a set of exponents f of x is a signomial with respect to these exponents, and I'm going to maximize the lower bound gamma subject to fx minus gamma being a SAGE function with respect to those exponents. And this does interesting things. So this is a...
Actually, so even for, in the special case where we have non-negative integer coefficients and we get polynomials,
Yeah.
then we can talk about the proof system of how do you
Yes,
prove
I will very much talk... Yeah.
So you're defining a proof system
I'm
here.
defining a proof system.
Is there
So for example, again, this is something I wanted to talk about. You can combine the two. Certainly sum of squares gives more concise proofs for non-negativity of certain polynomials that SAGE does not. But there are equally examples where this will give a more concise proof than sum of squares.
Ignore, the degree bounds of the proof system. Even for checking, polynomials non-negative, you have to go to rational functions sometimes. So I guess I'm asking, do you...
You can show that the SAGE methodology, I'll actually formally describe a hierarchy. I've just described a basic relaxation. I'll describe a hierarchy that will, in fact, be complete for polynomial problems. Alternative, but yeah, we will actually show this. But again, all phrased in the language of SPs because that's really what I'm interested in. But so this signomial consists of 6 terms and 3 variables. So the first 3 terms are what we fixed. The last 3 terms are what we chose randomly, and I'll describe that construction in the next slide. But this is, not obviously something that you can solve using geometric programming, certainly, trying to minimize the signomial because there are 2 negative terms there. So this is not a GP. We minimize this, produce a lower bound using SAGE, and we get that bound. And there is a way that I'll describe in the next few slides by which we obtain a point that certifies that the upper bound, the same value is also an upper bound. And that's something that I'll get to in a second. So this construction more generally was done as follows. We fixed the first 3 terms. The last 3 terms were chosen in the following way. The coefficients are zero mean Gaussians, and the exponents are uniform in this range. And the reason we chose the exponents to be in this range 0 through 3, and if you look at the first 3 exponents, they're much larger than that range, is to somehow, hopefully, get signomials that are actually bounded below. If you don't have signomials that are bounded below, and you have a framework to produce lower bounds, and you get negative infinity, you actually have no idea if your framework is somehow failing or if the signomial itself is unbounded below. So this was an attempt to produce a family of signomials that are hopefully bounded below. And in this random family, we applied this technique, and the SAGE relaxation ends up being tight in 60+% cases out of 80 random tries. Again, I want to emphasize that these stars are Gaussian, so they can be positive, negative, and so these certainly are not GPs. And what we had in the previous slide was an example of this. It obviously fails in some cases, and so one can now talk about trying to develop a hierarchy for these things. Before I talk about the hierarchy, I'll need to define a quantity. This is obtained by taking all bounded integer combinations of the exponents, where the weights sum up to at most p. And based on this definition, we have the following tighter lower bound. We maximize gamma subject to a positive function times f of x minus gamma being SAGE. This guy is positive because it's just a sum of exponentials. The exponents here times the exponents here give rise to things that consist of p plus 1 possible combinations of all the exponents. And that's why we have this exponent set here. And this is a tighter sufficient condition for global non-negativity than what I had a few slides ago. Previously, we just had that f of x minus gamma is SAGE with respect to E1. And now we have that this thing, raised to the power of p, has to be SAGE in E p plus 1. You can show that this is a lower bound on the optimal value because this is a sufficient condition for non-negativity. You can show that this is non-decreasing with respect to p. And we have the following completeness result. The one thing I'll mention before I actually describe the result is that this should be reminiscent, if you look at the polynomial world, of Pauli or Resnick type result, where you have uniform denominators and so forth. But the theorem is as follows. The sequence of lower bounds converges to the optimal value, provided these conditions are satisfied by the exponents. They're rational. The number of exponents is bigger than the dimension of the problem, the dimension of the variable x. This is not a very stringent condition. If this is not satisfied, you can always reduce the dimension of your problem. The second condition is that the exponents, the first n of the exponents are linearly independent. Again, not difficult. You can just group the first n of them, or group the largest linearly independent set into the first n, and that's okay. You can always add the 0 exponent. This essentially corresponds to a constant term. The last condition is what's interesting. I'll talk about why we need it a few slides later. But what you need is that the remaining exponents outside of the first n and the 0 are contained in the convex hull of the first n plus 1. Okay? So this is sort of a simple picture in 2 dimensions. If you have a Signomial optimization problem involving 2 variables, the first 2 are these ones, then you add 0, and all the other exponents ought to belong in that convex hull. There's a precise reason why we need this. Okay. So the dual viewpoint is promised, as I mentioned right at the beginning. We can reformulate an unconstrained SP, the minimization of something of that type, into the minimization of a linear functional subject to this convex set. And everything that I've talked about, all these relaxations, both the basic one as well as the hierarchy, can be viewed as producing tractable convex outer approximations to this set. Okay. So if you have a convex outer approximation of the set, it stands to reason that when you minimize C transpose V, you will get a lower bound. So that's a different way of seeing that everything that I talked about produces a lower bound.
What was the notion of convergence for the lower bound?
Notion of convergence? It converges from below. It's non-decreasing, so as P increases, it's the usual kind of completeness result.
Is there any bound on P in terms of n or the degrees?
I wish we could do that, but in general, I mean, those are hard problems even in the polynomial world. I'll have a bit to say about it then at the end, but no, even for very simple cases in polynomial optimization, the bounds that do exist tend to be pessimistic. These things and these sorts of relaxations end up doing far better than predicted frequently. So effective bounds in the hierarchy that actually reflect problem difficulty, I think is an interesting hard question. Okay, so the dual of the very basic SAGE relaxation can be viewed as follows. You minimize a linear function subject to this constraint set. This is what the basic SAGE relaxation does. And as I mentioned, that constraint set is an outer convex approximation to this set. And it's a constraint set specified in terms of relative entropies, all your exponents, and so forth. So this is the dual of that first level of that SAGE hierarchy. So based on this, it's now easy to see how you can potentially verify if the solution that you found using this method is actually the optimal solution of the original problem, or is a global minimizer of the original problem, right? You solve this, you get a V, and if that V lies in this set, you're done. Okay? And that's exactly described on the slide. You get an optimal V after solving this relaxed problem. You take logarithms because of this exponential, this collection of exponentials, and you ask that it satisfies an overdetermined system of linear equations. And if it does satisfy this, then you've exactly solved the original problem. And this is very much in spirit, by the way, if you've seen the literature in STP relaxations for polynomials. If you solve the basic, SOS, if you solve the STP corresponding to the basic SOS relaxation and your solution is rank 1 somehow, you've actually solved the original problem. This is very much an analog of that, except that now you have that this point belongs to this curve or the surface of exponentials. And if you have that property hold, you've actually solved the original problem. Moving to constrained SPs, I think the harder, more interesting story is with the unconstrained case in general with all this stuff. Moving to the constrained case, you have a collection of signomials specifying constraints now. That's the same sort of story. You can reformulate this via restricted non-negativity and maximize gamma subject to fx minus gamma being non-negative on the constraint set. And as before, we'll give sufficient conditions for restricted non-negativity, and that will give us a family of lower bounds. So for instance, you can maximize gamma subject to fx minus gamma minus this guy being SAGE. This is just sort of and if you wanted to prove a weak duality type argument, if you wanted to compute the Lagrangian dual of your original GP, you would do exactly this and ask that this thing be globally non-negative. You're replacing that with SAGE. Pretty standard. But even this does some interesting things. If you have this subjective function, again, 2 negative terms, it's an example from before, and you have the following constraint set, you get something that is in fact tight. What's interesting here, just a point and note, not necessarily interesting, is that this constraint set is convex. The objective function, though, does consist of negative signs. So this is, again, not a GP. Going to sort of a more general constraint set, not necessarily convex because it has lots of negative signs, negatives and positives mixed. We again see that this is tight. This was generated in the same sort of random fashion that the objective was generated in based on the description a few slides ago. And in fact, in the constraint case, we struggle to find examples, at least in this random ensemble, one objective, one constraints generated in the random way that I described a few slides earlier. We struggle to find examples where this very basic relaxation failed.
Here you're planting a very nice certificate that the function is globally non-negative, right? Just
this is not a nice this is a sufficient condition.
You're planting a very nice certificate. I can prove to you, I don't have to be f stage 01 that this thing is going to be. The point is, right, you're making the exponents of the positive parts very big, and the exponents in the negative parts smaller, and then in your constraint.
But that does not make the problem easy, right? If I threw this into a GP solver, there is no way you could actually produce a lower bound. And by the way, I'm not asking you to certify the non-negativity of this. I'm asking you to find minimize this function, or minimize this function subject to these constraints. And we have no methodology to actually do this. If we have multiple, it may look easy, but that doesn't mean that it is sort of trivial, or we have a direct methodology to do it.
Maybe to make James happy, can you show that the Hessian is indefinite here? Because that's another thing.
In this case, yes. We did something different. I think we found a line on which this was not convex. So that's, these are not trivial or easy problems.
Wait,
right?
It's not convex?
Yes, this is not convex. You can actually find. We've developed a convex relaxation framework for this that turns out to be tight in these cases. But this objective function is not convex. You can actually find a line segment with it.
That being convex on lines is the right geometry?
Absolutely. Convexity of a function is equivalent to it being convex on all lines.
No, but I mean instead some sort of tracing out a, exponential.
But if I'm being asked to prove that this is not convex, if I can show that it's restricted to some line, it's not convex, that's good enough, right? But in general, there may be a different geometry to these things. That could well be. Yeah.
Because there's no reason, when you talk about Bregman projections, the geodesics are not necessarily.
But this, I don't know that we need to get that complicated. I'm just answering a very simple question, which is that this function, we have a line where we know that it's not convex restricted to that line, so it's not a convex function. Yeah. So it's just answering a very simple question that was raised by Ben. Okay. So one can again talk about a hierarchy of relaxations in the constrained case. We have the same sort of bounded linear combinations, or bounded integer combinations of exponents as before. We have products of our constraints, and these will specify redundant constraints as a sort of standard in optimization. And you maximize, again, a lower bound subject to adding in all these redundant constraints and asking that these redundant inequalities also hold. And we use SAGE multipliers there. use SAGE here. I'm not going into the details of this because this is very similar to what's done in polynomial optimization, where you replace these Lagrange multipliers in the basic weak duality that I mentioned before by SAGE functions. You replace this by a SAGE function, and you can build a hierarchy based on this idea. This is a tighter sufficient condition for constrained non-negativity because you've added in all these redundant constraints. And as before, you can show that the sequence of lower bounds produced by this hierarchy also converges to the optimal value, provided essentially the following constraint hold, the following condition hold, that the constraint set is compact. So in the constraint case, we need this compactness assumption. This is the basic proof idea in the unconstrained as well as the constrained cases. This is the following. I mean, we need the following two notions from the algebraic geometry literature, that of a pre-prime and that of a module over pre-prime. The set of signomials with positive coefficients, polynomials as I mentioned before, forms a pre-prime because it's closed under additional multiplication. The set of SAGE functions forms a module over this pre-prime because multiplying a SAGE function by a polynomial still gives me a SAGE function. And so this forms a module over that pre-prime, and sort of within this framework, we appeal to positive Stellensatz that really talks about non-negativity certificates of for positive polynomials over modules. In the unconstrained case, that convex hull assumption that I had really ties in closely to certain Archimedeanity conditions. It's a very technical thing that shows up in appealing to these positive Stellensatz results. That's really the manifestation of it in the unconstrained case. In the constrained case, the compactness assumption is what allows us to satisfy this Archimedeanity assumption and these positive Stellensatz results. That's really what shows up in a lot of these representation theorems in real algebraic geometry, the sort of Archimedeanity condition that needs to be satisfied. And that's the reason for those two assumptions in the constrained and unconstrained cases. Okay, so there are some nice, interesting properties of these relaxations that are actually not revealed by these completeness results. These completeness results just basically say eventually you converge. You get to the right thing after solving something very large. But there are other very interesting properties that are not necessarily revealed by that theorem. The first is by sort of construction, GPs are exactly solved at the first levels of these hierarchies. Simple, basic point to be made. But it is an important one, in that anytime you develop a framework, you'd hope that easy problems continue to remain easy. And that's certainly the case here. But the first level also solves problems that go beyond GPs. So this was an example that we were able to minimize with more than 0 negative signs. There are 2 negative signs there. So we do end up solving problems beyond GPs. SPs also have, signomial optimization problems also have a nice invariance property. So if you take all the exponents in your problem, both in the objective and in the constraints, and apply a non-singular linear transformation simultaneously to all of them, the underlying SP remains unchanged. So the optimal value remains unchanged, non-negativity properties and so forth remain unchanged. And you'd like this to also be a feature of any methodology you develop for SPs. And it's certainly the case that SAGE decompositions sort of respect this invariance. A third sort of interesting property is the robustness of the SAGE relaxation to perturbing the exponents. So if you take this unconstrained SP, this unconstrained signomial, following from the examples before, that's sort of just written in a different way. 6 terms, we were tight. I'm going to leave the coefficients unchanged, but I'm going to perturb the exponents. So I've perturbed all the exponents slightly, and we get a closed signomial in some sense. And we continue to sort of remain tight, produce a solution that's close by, produce an optimal value that's close by, and so forth. So this sort of robustness is also something that you'd like of any framework you develop for SPs. And this is one sense in which SPs are very different in comparison to polynomial optimization problems. Because you'd like robustness with respect to the exponents too. If I have a small integer exponent, 2 for example, and I change 2 to 2 million divided by 1,000,001, it's very, very close to 2. But if I think of it as a polynomial problem, things sort of blow up. I mean, that's just not the right sense in which you want to think about SPs, especially if you care about robustness with respect to the exponents. We have a theorem that describes why SPs are actually robust. I won't go into the details of this. The main thing that I want to point out is something qualitative. The reason for all these properties, invariance under the application of a non-singular transformation of all the exponents, robustness with respect to perturbations of the exponents, and so forth, all really can be seen when you go back to the basic certificate that we employed right at the beginning for signomials with just one, with at most one negative term. And the exponents, if you think about it in the original signomial, appear as just linear equations. And so if you perturb these, if the original linear equations were somehow not degenerate in some sense, you will still get a nearby set of a nearby affine space, and so things are likely to be okay. And that's really the reason why we have robustness with respect to perturbing the exponents. We have invariance with respect to a simultaneous non-singular transformation applied to both sides. It really follows from that relationship. And that's really why all these nice properties actually hold. Okay. So let's do some contrast with polynomial optimization, a topic that's received a lot more attention. So we have SDP relaxations for polynomial optimization problems based on sum of squares decompositions. There is sort of a natural correspondence. In that world, you use sums of squares decompositions to certify non-negativity. Here we talk about SAGE signomials. There, sum of squares decompositions lead naturally to SDPs. Here, these guys lead naturally to relative entropy relaxations. So what are the comparative advantages of these frameworks? When is one maybe better than the other, and so forth, right? So here is an example of a signomial that is not SAGE. It's a signomial with 6 terms. It's globally non-negative because I can write it as a perfect square. So it's evidently non-negative. But this signomial is not SAGE, and the way we came up with it is based on some connection to H matrices that I can talk about later. So clearly, even if you restrict yourself to the limited family of polynomial optimization problems, or signomial problems where the exponents are small positive integers, SOS is doing something that's different from SAGE, and maybe SAGE is doing something that's a bit different from SOS. So what's really going on? The answer is, I don't completely know, but a few thoughts. So if you have SPs with rational exponents, in principle, these can be transformed to polynomial optimization problems over the orthant. So if you think about just such signomial programs, when is sum of squares useful for SPs? If you can transform the original SP to a polynomial optimization problem, hopefully with low degree terms, right? That's hopefully when you expect all that literature to be very, very useful. It may still, I think, be interesting to study combinations of SAGE and sum of squares, because, for example, the Motzkin polynomial, viewed suitably, is a SAGE function, but it's not a sum of squares, at least not directly a sum of squares, although you can certify its non-negativity with just one level up in the hierarchy. When might SAGE decompositions be useful? If your SP has exponents with large denominators, so clearing denominators potentially leads to very, very large degree polynomials in your resulting polynomial optimization problem. And so if you have SPs even with rational exponents, while they may be transformable to polynomial optimization problems in principle, the SAGE methodology is still useful because you care about different things. You care about robustness with respect to different kinds of perturbations and so forth.
So was there an algorithm for SAGE optimization?
For signomial programming, you mean? There were tons of methods in the optimization literature based on branch and bound and so forth. Sorry?
With your work?
Yeah.
Is there one?
There is one.
So what was the result? Yeah.
The result was that we have a hierarchy of relative entropy.
GP. Just
asking GP?
GPs. Yeah.
With Lasserre or Perillo, I know the complexity is n to the r. What is the complexity and what's
the complexity of a certain level in the hierarchy?
So what's the level of hierarchy?
What do you?
The power p, right?
The power p indexes the level in the hierarchy. For instance, in the unconstrained case, you have p and q, that indexes a power of the hierarchy. Maybe the constrained case is simpler to look at. This is the constrained case. I'm sorry, the unconstrained case. It's simpler to look at.
P is the?
P is the power here.
I think the question is, what do you use to actually solve this?
What do we use to solve this? Or, I mean, this is a convex optimization problem, and we just use sort of a basic interior point method to solve this. P is a positive integer. We raise this guy to the power P, multiply f of x minus gamma.
What's the complexity of this? It's like L to the P roughly?
It will be on the order of L to the P, yeah. L is the number of exponents.
Number of exponents. L to the P.
A number of?
Exponents in your SP.
No, I did mean this one.
Oh,
Like
L
the
is
number of
polynomial.
basically.
Number of exponents in your Signomial.
So if you count the dimension, it will be like n to the p. Right?
Or, yeah, L to the P, yes, yeah. And that's roughly what it ends up.
And again, it's
There you'll have Q as well, sure, yeah.
And convergence log of 1 over epsilon.
There's no epsilon here.
It's an optimization, no?
This is an optimization problem. I've talked about this optimal value.
He said Jeep is asking, what is the algorithm for solving geometric programs?
Right. What is it? You fix an epsilon and you are able to solve to that accuracy in
What algorithm do you use?
interior point. And it's log of 1 over, yeah.
Oh, interior point works for this.
Interior
I
point
think
works for this. This is,
It's better than log of 1 over epsilon. I think you get quadratic convergence, right? You use the primal dual method. It's like you.
yes, we used only a primal only method and so forth.
That's
But,
going to be worse.
yeah.
Yeah.
But yeah, I mean, so this is a convex program with a nice barrier function and so forth. So yeah, that is the algorithm. Yeah. I mean, I guess I swept all that under the rug when I said that the relative entropy function is jointly convex. And
Oh, that's enough to give everything.
not in general, no, because convexity just because the function is convex doesn't mean it's tractable to compute. But this is a nice convex function in some sense.
There are really nice algorithms for geometric programming. Okay. And so
Yeah. Really, I mean, a GP is, I don't know, some might dispute this, but a GP is roughly on the same order of complexity as an LP, in some sense of the right size and so on.
So this is also the intuition why you use the relative entropy of order 1 in this relaxation.
I use the relative entropy of order 1
At the level 1.
at the level 1. Yeah. What was the I'm sorry, I don't follow the question.
Like there's whole families of relative entropies, so I just wanted to kind of understand why this one is special, like why kind of the standard relative entropy, which is also called order 1, is kind of special in this setting.
Why it's kind of special? Well,
Is this because of the exponential, or just because it becomes tractable then, or?
I'm still not sure I follow the question because these larger levels of the hierarchy still involve the relative entropy function, but just computed over a larger number of variables. So I don't know when you...
Comes up as the conjugate of
Oh, there's other relative... That's the question. Okay, yes, no. This was the relative entropy that naturally parameterizes an AMGM inequality, and that's the reason we used it. Yeah. I mean, there are other... I don't know in the classical case if there are other relative entropies, perhaps based on other entropies. Yeah.
Yeah, there are.
No, this is not the quantum world. Or, yeah. Where did I stop? Yes.
You gave also this example of like the Motzkin polynomial of having small proofs here. So what about examples where you sort of need very high degree to prove some system of polynomial is not feasible? Do some of those examples translate to
Coming
much
up.
lower
Right here.
complexity?
This is the next one. Last example. Sorry. So, I mean, I'm going to state it more in terms of sets. So consider the following set where A and B are coefficients of this univariate polynomial. And I want all possible A's and B's, two-dimensional set, convex set, where this univariate polynomial is globally non-negative. It's SDP representable, it's a projection of a slice of the PSD cone, convex and algebraic and so forth. As far as I know, the size of any SDP I was able to write down grows with D. So as I increase this D is a positive integer here, the size of any SDP description of this seems to grow with D.
But SDP description means exact?
Exact SDP representation of the set. By that I mean a projection onto 2 dimensions of a larger SDP cone slice with an affine space.
It exists.
It exists
Oh, you
based
say-
on sum of squares, yeah. That's an existence proof. This is just a univariate polynomial. Very, very simple.
But there's no proof, though, that the size of the SDP grows.
There's no proof, yes. I don't have a proof, but I think it ought to be possible because the boundary of this...
have more intermediate terms for...
No, in this case, it's just algebraically will follow. Right?
Yeah, because if you take this convex set, the boundary ends up having very, very large degree. But there is a very nice description of exactly that set using relative entropy. So all A's and B's that satisfy this condition, so the existence of a nu, such that this relative entropy inequality holds where A and B show up, and that linear equation holds, exactly characterizes this set. So we have a convex semi-algebraic set, something that's semi-definite representable, contrived of course, but still I think it makes a point that you have a lift and project method where the lift involves fundamentally something that's non-algebraic. When you project it down, you get something that is semi-algebraic. But the sort of non-algebraic structure upstairs leads to a much more efficient description that does not grow in size with D of the original set.
Wait, so that equation you said D minus 1 times mu 1 equals mu 2?
Yep.
So the only flexibility is the length of the vector, I guess. Like
nu1 and nu1 nu is in two-dimensional space. So nu1 is the first coordinate, nu2 is the second coordinate, nothing else.
I mean, so the AMGM proof underneath it is sort of highly unbalanced, which is part,
Yes, that's exactly it, and that's the last slide of the talk. Sorry. So if you want to prove the AMGM inequality with fixed rational weights, you can give a sum of squares proof of the AMGM inequality. But depending on the kind of rational weights you have, that proof can be very, very long. But relative entropy searches over these weights to certify non-negativity via AMGM. And in some situations, I think this idea could be much more powerful, even for polynomial problems.
So that's why Motzkin's example...
Motzkin is very much, but it's a low-degree example of it, but it's also an illustration. Yeah, very much so.
For example, compare, let's say, the sum of squares proof of something like Hülder's inequality, and
the AMGM proof, perhaps. That's very much. That's a good example.
Very highly unbalanced.
Exactly. That's very much an example of this. So to summarize, I don't think I'll say much more. Maybe the one point I should mention is that relative entropy optimization, in the sense that we really exploit the joint convexity of relative entropy with respect to both arguments, ends up being useful in a bunch of other settings. I'm happy to talk about these offline. Thank you. Aram has, or should we take it offline? I don't know. You decide.
Well, this probably will go nowhere very quickly, but instead of a sum of exponentials, if you had a trace of an exponential of some matrix...
Very interesting question, yeah.
Anything you can do with that?
We have thought about this. I can talk a bit offline. You can certify lower bounds for very, very special problems of that type using quantum relative entropy, but it's still something I don't understand completely. I can tell you what I know, but yeah.
Questions, comments? Sanjay?
So, I guess I don't know so much anything about GP, but it seems somehow just the way the phrasing seems it should be highly non-robust numerically, but it is robust. Everything.
It is. Yeah.
Exponentials and so on. I see.
Yeah.
Well, you went very fast over the robustness theorem, so.
I could. It was very wordy. That's the reason.
This is the notion of robustness.
This is a notion of robustness. Robustness in the SAGE context.
Algorithmic robustness of the geometric program. Stability.
Yeah, the stability of just GPs with respect to is generally well understood, and these are stable.
That ridiculous book, an interior point method. It's one of the ones that they do.
Yeah.
That's one of the prime examples.
It is. I mean, it is well conditioned, if you will.
CS people don't often know that literature. Just for your talk. Yeah. So.
Okay. I'll certainly talk more about that. Yeah.
We can all read that book tomorrow.
There will be a test.
One more question, I guess.
You showed some examples where like your hierarchy is tight at the first level. So do you understand those, or I mean,
other than giving sort of a self-referential things, those are things that are written as SAGE functions or whatever. No, not really.
Because you drew the parameters randomly. Is randomness anything related to?
I don't think so. I think in that case it was not just randomness, but the specific construction. Some of the exponentials were large and fixed, the others were small and random. That played a role, certainly. Yeah, I wish I could say more. It's certainly something we're interested in, but...
Did I miss an example?
The absolute last one.
That F1 gave a better answer than F0?
That can never happen. At least if you solve it to, arbitrary accurate. He's talking about the first level of the hierarchy doing worse than the second, doing better than the second level of the hierarchy.
So
No, it's F1 better than F0.
F1 better or worse?
I thought if you make more levels, you get a.
Yes, that is true.
Did you show any numerical example?
Not of that. I have a backups.
You have a proof essentially because
you have a proof. This is an example where.
And you know that eventually it becomes tight.
Yes, and eventually it becomes tight. This is one of the backup slides, a simple example of. This doesn't mean anything, those are just numbers, but at least.
I'm curious that for your random examples, how high you had to go to get.
Well, like I said, at least in that ensemble, 60% of them were tight at the very first level.
Yeah.
This was one example that was not tight. We tried the second level. I don't think this is tight either. But perhaps, yeah.
Good. If we have further questions, you can catch Venkat probably the rest of the week.